Welcome to today's paper reading. Today's paper is titled, Offsite-Tuning, Transfer Learning Without Full Model. This paper was published on AR14 by Guangxuan Xiao and colleagues from the Massachusetts Institute of Technology. The abstract highlights the challenges in transfer learning, particularly with proprietary foundation models. Users face privacy concerns and high computational costs when fine-tuning these models. To address these issues, the authors propose Offsite-Tuning, a framework that allows for efficient and privacy-preserving transfer learning without requiring access to the full model. This method involves the model owner sending a lightweight adapter and a lossy compressed emulator to the data owner, who then fine-tunes the adapter. The results show that offsite-tuning can achieve comparable accuracy to full model fine-tuning, with significant improvements in speed and memory usage. Figure 1 illustrates the differences between traditional fine-tuning methods and offsite-tuning. In traditional fine-tuning, users send labeled data to model owners, which raises privacy concerns and high computational costs. A. Sending the full model to the data owner is impractical due to resource constraints and threatens model ownership. B. Offsite-tuning provides a privacy-preserving and efficient alternative by using a lightweight adapter and a lossy compressed emulator, allowing fine-tuning without full model access. C. Offsite-tuning is a method designed to adapt foundation models to specific tasks without requiring access to the full model. This approach is highly resource-efficient and ensures that both data and model privacy are preserved. In evaluations, offsite-tuning has demonstrated performance comparable to traditional fine-tuning methods, achieving up to 6.6 times faster processing and 5.6 times less memory usage. This makes it possible to fine-tune large models like OPT 6.7b and Bloom 7.1b on a single GPU. Overall, offsite-tuning offers a practical solution for applying foundation models more safely and efficiently across a wider range of real-world applications, benefiting data owners by enabling faster and less resource-intensive model adaptation. Foundation models, such as GPT-3 and CLIP, are pre-trained on extensive datasets and primarily utilized through transfer learning. Parameter-efficient fine-tuning methods, like adapter tuning and LoRa, adapt these models to specific tasks by updating only a small number of parameters. Offsite-tuning is a novel approach that ensures privacy by not requiring full model weight sharing, using adapters and emulators for efficient fine-tuning. Figure 2 illustrates the process of offsite-tuning, a method designed to adapt foundation models to downstream tasks without requiring access to the full model weights. On the left, traditional fine-tuning is shown, which necessitates the full model weights and places both the model and data in one location. This approach can compromise data privacy and is resource-intensive. On the right, offsite-tuning is depicted, where the model owner sends an adapter and a compressed emulator to the data owner. The data owner then fine-tunes the adapter using the emulator's assistance on the downstream data. The fine-tuned adapter is returned to the model owner, who integrates it into the full model to create an adapted foundation model. This method ensures privacy for both the data and model owners, as neither full models nor data are shared. Additionally, the use of a compressed emulator makes the process more efficient. In transfer learning, privacy is a significant concern. The data owner cannot share their labeled training data, and the foundation model owner cannot share their full model. The challenge is to tune the model on the data owner's data without accessing the full model weights. Given a foundation model M parameterized by theta and a downstream dataset D, fine-tuning typically yields M theta plus increment. To address privacy, we introduce a substitute model M** operator, which is smaller and weaker than M, ensuring that sharing M** operator does not compromise the foundation model's ownership. Data owners then optimize this substitute model on their dataset, yielding M** operator theta operator plus increment operator. The goal is to achieve similar performance to directly optimizing M on the dataset, without exposing M itself. To evaluate the method, we use metrics such as zero-shot performance, emulator performance, and plug-in performance. In the offsite-tuning framework, the foundation model M is divided into a small, trainable adapter A and a frozen component D. This division allows for downstream adaptation while protecting the model's integrity. Lossy compression is applied to the frozen component, resulting in an emulator E*. Downstream users are provided with the combination of the adapter and the emulator, E*, enabling them to perform model tuning by updating A. The updated adapter is then returned to the original model owner, who integrates it into the model to achieve improved performance on downstream datasets. This process ensures that model ownership is preserved and efficiency is enhanced. Figure 3 presents an ablation study focusing on the number and position of adapter layers within language models. The study compares the performance of fine-tuning only the top layers, only the bottom layers, and both the top and bottom layers while keeping the rest of the layers frozen. The results indicate that fine-tuning both the top and bottom layers, known as the sandwich design, significantly outperforms fine-tuning only the top or bottom layers, given the same number of trainable layers. This finding highlights the effectiveness of the sandwich design in enhancing the performance of language models through fine-tuning. Table 1 presents the results of Offsite-Tuning, OT, on various tasks, showing that the OT plugin significantly enhances zero-shot, CS, performance across all evaluated tasks. Notably, there is a consistent performance gap observed between the emulator fine-tuning and the plugin, which underscores the effectiveness of Offsite-Tuning in preserving the privacy of the original proprietary model. This means that users cannot achieve the same performance using the emulator alone, thereby safeguarding the original model's proprietary information. The table highlights the slight decreases in performance compared to full fine-tuning, FT, yet the overall improvement in zero-shot capabilities is substantial. In this section, we discuss the experiments conducted to evaluate offsite-tuning on both language and vision models. For language models, we used GPT-2, OPT, and Bloom, and evaluated them on the Wikitext dataset and 8 question-answering benchmarks. Performance was measured in terms of perplexity and accuracy. For vision models, we focused on CLIP and EVA, and assessed their performance on 6 fine-grained image classification datasets, with accuracy as the metric. The implementation was based on the Hugging Face Transformers library, using the Atom W optimizer and a cosine learning rate scheduler. A grid search was employed to find the optimal learning rate. Figure 4 presents an ablation study on various compression methods used for creating an emulator. The study highlights that the layer drop method outperforms other methods in 2 key areas. Firstly, it effectively maintains the plugin performance while significantly reducing the size of the emulator. Secondly, it creates a noticeable gap between the plugin performance and the emulator performance, thereby preserving the privacy of the model owner. This suggests that the layer drop method is an effective strategy for developing efficient and privacy-preserving emulators. Table 2 presents the results of Offsite-Tuning, OT plugin, on large language models, specifically OPT 6.7b and Bloom 7.1b. The data shows that OT plugin significantly enhances zero-shot, CS, performance across various tasks, even without access to the full model. A notable observation is the consistent performance gap between the emulator and plugin, which indicates that Offsite-Tuning effectively preserves the privacy of the original proprietary model. This preservation of privacy is crucial as it ensures that users cannot use the emulator to achieve the same level of performance, thereby safeguarding the integrity and confidentiality of the model and its data. Table 3 presents the effectiveness of Offsite-Tuning on vision foundation models, specifically EVA and CLIP, both utilizing ViTG backbones with 1 billion parameters. The table shows % accuracy scores across various settings and datasets. Key findings include the high accuracy of the EVA ViTG model at 99.59%, the OT plugin achieving 99.63% accuracy, and the CLIP ViTG model with 99.33% accuracy. These results indicate that Offsite-Tuning can effectively adapt these models while maintaining high performance levels. Table 4 illustrates the effect of distilling the emulator on the performance of Offsite-Tuning, specifically in terms of improving plugin performance while ensuring the privacy of the full model. The scores presented are validation perplexities on the Wikitext2 dataset, where lower values indicate better performance. The table shows that with distillation, the plug-in performance is enhanced, as evidenced by the reduced perplexities for both GPT-2XL and OPT-1.3b models. Despite these improvements, there remains a noticeable gap between the plug-in and emulator performance, which indicates that the full model's privacy is still effectively preserved. This suggests that further improvements in parameter efficiency for the emulator could be achieved with additional computational resources for more distillation epochs. Table 5 illustrates the combination of offsite-tuning with parameter-efficient fine-tuning techniques, showing validation perplexities on the Wikitext2 dataset. For the GPT-2XL model, the number of trainable parameters is significantly reduced from 1475 million to 83,000 with techniques like adapter tuning and LoRa, while maintaining competitive performance. Similarly, for the OPT-1.3b model, the reduction is from 1208 million to 106,000 trainable parameters. These results highlight the effectiveness of combining offsite-tuning with parameter-efficient fine-tuning methods to achieve substantial parameter reduction without compromising performance. Table 6 presents the efficiency gains of offsite-tuning on a single A6000 GPU, focusing on fine-tuning speedup and peak memory savings. The data reveals that when combined with LoRa, offsite-tuning achieves a significant 6.5x speedup and a 5.6x reduction in memory usage. This efficiency is crucial for fine-tuning large foundation models on resource-constrained devices. The throughput rates, measured in tokens per second, show substantial improvements, reaching up to 8,525 tokens per second, demonstrating the practical benefits of offsite-tuning in enhancing both speed and memory efficiency. Offsite-tuning is particularly effective for personalizing large language models on edge devices, which is beneficial for applications like voice assistants and chatbots. This method allows users to adapt a large language model to their personal information directly on their devices, enhancing efficiency and privacy by avoiding data transmission to a server. The adapted model can generate personalized text, such as emails and messages. Additionally, offsite-tuning can be applied in sensitive domains like healthcare, where it can adapt a large language model to patient records without sharing the records with the model owner, thereby generating personalized medical reports. This approach also protects the privacy of the model owner by not requiring them to share their full model with the data owner. In this work, the focus is on addressing data privacy and efficiency concerns during the adaptation or fine-tuning of foundation models, rather than during inference. Privacy during inference can be addressed through other methods. However, there are limitations to this approach, such as the size of the emulator for large models like GPT-3 and the cost of compression through distillation techniques. There is also a need for future research to investigate potential information leakage and to further explore the theoretical foundation of the emulator and adapter design. In conclusion, the authors propose offsite-tuning, a framework designed to preserve privacy while efficiently adapting foundation models to various downstream tasks. This method does not require access to the full model parameters, making it particularly effective for large-scale models in both language and vision domains. Offsite-tuning allows users to customize these models without the risk of compromising data or model privacy, thereby enhancing both efficiency and security in transfer learning applications. Thank you for watching.